The faint young sun paradox or faint young sun problem describes the apparent contradiction between observations of liquid water early in Earth's history and the astrophysical expectation that the Sun's output would be only 70% as intense during that epoch as it is during the modern epoch. The issue was raised by astronomers Carl Sagan and George Mullen in 1972. Proposed resolutions of this paradox have taken into account greenhouse effects, astrophysical influences, or a combination of the two. An unresolved question is how a climate suitable for life was maintained on Earth over the long timescale despite the variable solar output and wide range of terrestrial conditions. Solar evolution. Early in Earth's history, the Sun's output would have been only 70% as intense as it is during the modern epoch, owing to a higher ratio of hydrogen to helium in its core. Since then the Sun has gradually brightened and consequently warmed the Earth's surface, a process known as radiative forcing. During the Archean age, assuming constant albedo and other surface features such as greenhouse gases, Earth's equilibrium temperature would have been too small to sustain a liquid ocean. Astronomers Carl Sagan and George Mullen pointed out in 1972 that this is contrary to the geological and paleontological evidence. The Sun is powered by nuclear fusion, which for the Sun can be represented in the following way: 4 1 H He 4 plus 2 E plus 2 nu. Display style CE 4 caret 1 H 2 caret 4 He plus 2 E plus 2 nu 4 1 H plus E minus He 4 plus E plus 2 nu. Display style CE 4 caret 1 H plus E 2 caret 4 He plus E plus 2 nu. In the equations above, E plus is a positron, E is an electron and nu represents a neutrino, nearly massless. The net effect is threefold: a release of energy by Einstein's formula delta E equals mc2, an increase in the density of the solar core, since the final product is contained in one nucleus as opposed to between four different protons, and an increase in the rate of fusion since higher temperatures help increase the collision speed between the four protons and boost the likelihood that such reactions take place. The net effect is an associated increase in solar luminosity. More recent modeling studies have shown that the Sun is currently 1.4 times brighter today than it was 4.6 billion years ago (Gaia), and that it has brightened roughly linearly since then with time, though it has accelerated slightly. Despite the reduced solar luminosity 4 billion 4 times 109 years ago and with greenhouse gas, the geological record shows a continually relatively warm surface in the full early temperature record of Earth, with the exception of a cold phase, the Huronian glaciation, about 2.4 to 2.1 billion years ago. Water-related sediments have been found dating to as early as 3.8 billion years ago. This relationship between surface temperature and the balance of forcing mechanisms has implications for how scientists understand the evolution of early life forms, which have been dated from as early as 3.5 billion years. Greenhouse gas solutions. Ammonia as a greenhouse gas. The faint young sun paradox may be resolved by accounting for the carbon cycle. Sagan and Mullen even suggested during their descriptions of the paradox that it might be solved by high concentrations of ammonia gas, NH3. However, it has since been shown that while ammonia is an effective greenhouse gas, it is easily photochemically destroyed in the atmosphere and converted to nitrogen and hydrogen gases. It was suggested, again by Sagan, that a photochemical haze could have prevented this destruction of ammonia and allowed it to continue acting as a greenhouse gas during this time. However, this idea was later tested using a photochemical model and discounted. Furthermore, such a haze is thought to have cooled the Earth's surface beneath it and counteracted the greenhouse effect. Carbon dioxide as a greenhouse gas. It is now thought that carbon dioxide was present in higher concentrations during this period of lower solar radiation. It was first proposed and tested as part of Earth's atmospheric evolution in the late 70s. An atmosphere that contained about 1,000 times the present atmospheric level or PAL was found to be consistent with the evolutionary path of the Earth's carbon cycle and solar evolution. The primary mechanism for attaining such high CO2 concentrations is the carbon cycle. On large timescales, the inorganic branch of the carbon cycle, which is known as the carbonate-silicate cycle, is responsible for determining the partitioning of CO2 between the atmosphere and the surface of the Earth. In particular, during a time of low surface temperatures, rainfall and weathering rates would be reduced, allowing for the buildup of carbon dioxide in the atmosphere on timescales of 0.5 million years (MYR). Specifically, using 1D models, which represent the Earth as a single point instead of something that varies across 3 dimensions, scientists have determined that at 4.5 Ga, with a 30% dimmer sun, a minimum partial pressure of 0.1 bars of CO2 is required to maintain an above-freezing surface temperature. At a maximum, 10 bars of CO2 has been suggested as a plausible and upper limit. The exact amount of carbon dioxide levels is still under debate, however. In 2001, Sleep and Zonal suggested that increased weathering on the seafloor on a young, tectonically active Earth could have reduced carbon dioxide levels. Then in 2010, Rosing et al. Analyzed marine sediments called banded iron formations (BIFs), and found large amounts of various iron-rich minerals, including magnetite (MULTIVALENTFE3O4), an oxidized mineral alongside siderite iron carbonate, and reduced mineral, and saw that they formed during the first half of Earth's history and not afterward. The minerals' relative coexistence suggested an analogous balance between CO2 and H2. In the analysis, Rosing et al. Connected the atmospheric H2 concentrations with regulation by biotic methanogenesis. Anaerobic, single-celled organisms that produced methane CH4 may therefore have contributed to the warming in addition to carbon dioxide. Other proposed explanations. A minority view, propounded by the Israeli-American physicist Nir Shaviv, uses climatological influences of solar wind, combined with a hypothesis of Danish physicist Henrik Svensmark for a cooling effect of cosmic rays, to explain the paradox. According to Shaviv, the early Sun had emitted a stronger solar wind that produced a protective effect against cosmic rays. In that early age, a moderate greenhouse effect comparable to today's would have been sufficient to explain an ice-free Earth. Evidence for a more active early Sun has been found in meteorites. The temperature minimum around 2.4 billion years goes along with a cosmic ray flux modulation by a variable star formation rate in the Milky Way. The reduced solar impact later results in a stronger impact of cosmic ray flux (CRF), which is hypothesized to lead to a relationship with climatological variations. Topic: Mass loss from Sun. It has been proposed several times that mass loss from the faint young Sun in the form of stronger solar winds could have compensated for the low temperatures from greenhouse gas forcing. In this framework, the early Sun underwent an extended period of higher solar wind output. This caused a mass loss from the Sun on the order of 5–10% over its lifetime, resulting in a more consistent level of solar luminosity as the early Sun had more mass, resulting in more energy output than was predicted. In order to explain the warm conditions in the Archean era, this mass loss must have occurred over an interval of about 1 billion years. Records of ion implantation from meteorites and lunar samples show that the elevated rate of solar wind flux only lasted for a period of 0.1 billion years. Observations of the young Sun-like star Pi 1 Ursae Majoris matches this rate of decline in the stellar wind output, suggesting that a higher mass loss rate cannot by itself resolve the paradox. Changes in clouds. If greenhouse gas concentrations did not compensate completely for the fainter Sun, the moderate temperature range may be explained by a lower surface albedo. At the time, a smaller area of exposed continental land would have resulted in fewer cloud condensation nuclei both in the form of wind-blown dust and biogenic sources. A lower albedo allows a higher fraction of solar radiation to penetrate to the surface. Goldblatt and Zonal 2011 investigated whether a change in cloud fraction could have been sufficiently warming and found that the net effect was equally likely to have been negative as positive. At most the effect could have raised surface temperatures to just above freezing on average. Another proposed mechanism of cloud cover reduction relates a decrease in cosmic rays during this time to reduced cloud fraction. However, this mechanism does not work for several reasons, including the fact that ions do not limit cloud formation as much as CCN, and cosmic rays have been found to have little impact on global mean temperature. Clouds continue to be the dominant source of uncertainty in 3D global climate models, and a consensus has yet to be reached on exactly how changes in cloud spatial patterns and cloud type may have affected Earth's climate during this time. Gaia hypothesis. The Gaia hypothesis holds that biological processes work to maintain a stable surface climate on Earth to maintain habitability through various negative feedback mechanisms. While organic processes, such as the organic carbon cycle, work to regulate dramatic climate changes, and that the surface of Earth has presumably remained habitable, this hypothesis has been criticized as intractable. Furthermore, life has existed on the surface of the Earth through dramatic changes in climate, including snowball Earth episodes. There are also strong and weak versions of the Gaia hypothesis, which has caused some tension in this research area. On other planets. Mars. Mars has its own version of faint young sun paradox. Mars's terrain shows clear signs of having liquid water on the surface, which include outflow channels, gullies, and recurring slow lineae. These geomorphic features suggest Mars had an ocean on its surface and river networks that resemble current Earth's during the late Noachian 4.1 to 3.7 Ga. It is unclear how Mars's orbital pattern, which places it even further from the Sun, and the faintness of the young Sun could have produced what is thought to have been a very warm and wet climate on Mars. Scientists have not reached a consensus on how exactly which geomorphological features can be attributed to shorelines and other markers of water flow and which may have been caused by other phenomena such as volcanic flow. Given the orbital and solar conditions of early Mars, a greenhouse effect would have been necessary to boost surface temperatures at least 65 K in order for these surface features to have been carved by flowing water. A much denser, CO2-dominated atmosphere has been proposed as a way to produce such a greenhouse effect. This would depend upon the carbon cycle and the rate of volcanism at that time throughout pre-Noachian and Noachian, which is not well known. Volatile outgassing is thought to have occurred during these periods. One way to ascertain whether Mars possessed a thick CO2-rich atmosphere is to look at carbonate deposits. A primary sink for carbon in the Earth atmosphere is the carbonate-silicate cycle. It is however hard for CO2 to build up in the Martian atmosphere in this way because it would likely condense out before reaching partial pressures necessary to produce a sufficient greenhouse effect. An alternative possible explanation posits intermittent bursts of powerful greenhouse gases, like methane. Carbon dioxide alone, even at a pressure far higher than the current one, cannot explain temperatures required for presence of liquid water on early Mars. Venus. Venus's atmosphere is composed of 96% carbon dioxide, and during this time, billions of years ago, when the Sun was 25 to 30% dimmer, Venus's surface temperature could have been much cooler, and its climate could have resembled current Earth's, complete a hydrological cycle, before it experienced a runaway greenhouse effect. Temperature evolution on Earth. See also: Cool early Earth, effective temperature of a planet, dependent on reflectivity of its surface and clouds. Isua Greenstone Belt, Paleoclimatology, Snowball Earth, Carbonate silicate cycle, Gaia hypothesis.